What truly exists beyond the event horizon of a black hole? This audio course is designed to explore the most profound mysteries of these cosmic behemoths, from the paradox of naked singularities to the conundrum of lost information. I invite you to join me on an expedition to the very edge of physics, a realm where our conventional understanding of space, time, and reality itself completely unravels. Picture a region of space where gravity has become so overwhelmingly powerful that even light cannot break free. This is the essence of a black hole, an ultimate point of no return, where the physical laws that govern our universe appear to cease to exist. On this journey, you and I will investigate how these obscure giants come into being and what fundamentally distinguishes them from all other objects in the heavens. Black holes are far more than just compelling elements of science fiction. They are a fundamental reality that holds a critical function in the cosmos. We have now observed these objects at the core of countless galaxies, our own Milky Way included. So, what are the implications for the evolution of the universe? How do these immensely powerful entities shape the formation of galaxies and the very fabric of the cosmos? The notion that a black hole might serve as a conduit to other dimensions, or perhaps a gateway for navigating through time, sounds like it was lifted directly from a novel. However, these very theories are capturing the serious attention of physicists who are asking if black holes could be more than just cosmic devourers of matter. Is it possible they are passages to parallel universes, challenging our comprehension and suggesting our reality is merely one piece of a much grander existence? Beyond their enigmatic nature, the gravity of a black hole fundamentally challenges our perception of time and space. In their vicinity, time behaves in peculiar ways, a phenomenon that forces us to reconsider time not as a straight, unwavering line, but as a flexible dimension that can be bent and warped. This concept naturally leads us to wonder about time travel, prompting us to ask if we could one day navigate the timeline as if we were sailing on an ocean. Another concept that shattered our traditional view of black holes came from the brilliant mind of Stephen Hawking, Hawking radiation. What if I told you that these cosmic giants are not immortal and can, in fact, gradually evaporate over immense timescales? This revolutionary idea has opened entirely new avenues in the study of these phenomena, proving that every answer we find only leads to more profound questions. The life of a black hole begins with incredible drama, originating from the death of colossal stars in cataclysmic events known as supernova explosions. But what follows their violent birth? The evolution of a black hole is a captivating cycle, a process that continues to reveal more about its intrinsic nature and its ultimate purpose within the grand scheme of the universe. Furthermore, the link between black holes and dark energy presents a fascinating frontier of research, one that may help us grasp the accelerating expansion of our universe. Is it possible that these two powerful phenomena are interconnected in ways we have yet to imagine? As we delve into these connections, we enter a territory defined by speculation, wonder, and the furthest reaches of scientific theory. Popular culture has generated numerous myths about black holes, frequently casting them as monstrous vacuum cleaners that indiscriminately consume everything they encounter. But how much truth is there to these portrayals? Science provides a far more subtle and thrilling viewpoint, dismantling these misconceptions to uncover the true character of these celestial objects. Finally, we will contemplate the philosophical and ethical questions that black holes present regarding our comprehension of the cosmos and our own significance within it. What does it say about humanity that such vast unknowns exist? The quest to resolve these questions propels us on a voyage of discovery that extends beyond science and into a deeper understanding of ourselves. As we move forward in this exploration, you will see that the universe of black holes is a vast ocean of knowledge, filled with mysteries and wonders. It is our curiosity that serves as the engine for this journey, compelling us to keep exploring, to keep questioning, and to keep discovering. So, I invite you to accompany me on this incredible voyage into the dark and profound secrets of black holes, where every star and every galaxy has a story just waiting to be told. At its most fundamental level, a black hole is a location in spacetime where the pull of gravity is so intense that nothing, not even light, has the ability to escape. To truly appreciate these most fascinating and mysterious phenomena in the universe, we must first understand how such a strange and potent object can possibly form in the cosmos. Imagine an immense star, a dazzling celestial body that has finally burned through all of its nuclear fuel. Without the outward push of fusion, its core gives way to an incredibly powerful inward force, gravity, which begins to pull everything relentlessly toward its center. In its last moments, the star erupts in a magnificent explosion called a supernova, leaving behind a dense remnant that, if it possesses enough mass, will collapse into a black hole. What truly defines a black hole is its extraordinary density. It can have a mass many times that of our Sun, yet all of it is squeezed into an infinitesimally small space. This incredible concentration of matter generates a gravitational field so powerful that once you cross its invisible threshold, known as the event horizon, there is absolutely no turning back. It is akin to a river approaching a massive waterfall. Past a certain point, the current is too strong to fight. One of the most intriguing qualities of black holes is that they come in different varieties. While several types exist, the most commonly known are stellar black holes, which are the remnants of massive stars, and the colossal, supermassive black holes. These giants are believed to reside at the heart of nearly every major galaxy, including our very own Milky Way. Intermediate mass black holes are less common and remain a subject of active investigation, as each classification possesses distinct properties. Studying them offers valuable insights into the cosmic timeline of our universe. Let's now turn our attention to the event horizon, a concept absolutely essential for grasping what a black hole is. You can picture the event horizon as being similar to the edge of a vast, dark lake. You can approach and observe the water, but once you cross a certain point, a return to the safety of the shore becomes impossible. For a black hole, passing beyond the event horizon signifies entry into a domain where our known principles of physics start to unravel and twist. Deep within this boundary resides the singularity, a point where gravity intensifies to infinity and space-time becomes warped in ways that our current scientific models are unable to depict. It represents a location where the fundamental laws of the cosmos seemingly cease to apply, presenting a profound puzzle that defies our comprehension of what truly occurs there. The reality is that the nature of the singularity remains unknown, making it a focal point of intense scientific research and debate. Fascinating questions about the fabric of space and time also arise from a black hole's immense gravity. According to Einstein's theory of relativity, gravity distorts the space-time surrounding it. Consequently, a clock positioned near a black hole would measure time differently from one situated at a great distance. This phenomenon means that in the vicinity of a black hole, time itself can flow at a slower rate. If you could journey close to one, you might find that while mere hours elapse for you, entire years have passed for the rest of the universe. Another captivating phenomenon involves tidal effects. Consider how a tranquil ocean can be whipped into a furious storm, generating colossal waves. In a similar fashion, a black hole's powerful gravitational field can stretch and squeeze objects in its proximity through a process famously called spaghettification. This is precisely the fate that befalls certain stars when they wander too close, as they are violently torn asunder in a truly spectacular cosmic event. We also have the concept of Hawking radiation, a groundbreaking contribution from Stephen Hawking, who theorized that black holes are not completely black. He proposed that they are capable of emitting a faint type of radiation, which, over immense stretches of time, could lead to their complete evaporation. This insight fundamentally changed our perspective, indicating that black holes might not be eternal fixtures, but could possess a finite life cycle. From here, we can explore an even more thrilling idea: wormholes. A number of scientists speculate that black holes could serve as conduits, linking disparate regions of the universe, or perhaps even connecting to entirely different universes. Although this may sound like something straight out of science fiction, the notion that a black hole might act as a gateway to another reality sparks the imagination and presents infinite possibilities regarding the true nature of space and time. The relationship between black holes and time continues to be a source of immense curiosity. Were it possible to traverse one, our perception of time could be radically altered, which naturally leads to speculation about time travel. Could these cosmic phenomena allow us to revisit the past or leap into the future? Science has yet to provide conclusive answers, but the investigation into these profound ideas is an ongoing endeavor. As researchers pioneer new technologies, including more powerful telescopes and methods for gravitational wave detection, our capacity for observing black holes grows substantially. Every new discovery inches us closer to solving their deep mysteries and appreciating their crucial role in the grand narrative of the universe's development. Black holes are much more than just inert dark spots in the cosmos. They exert a significant influence on the formation of galaxies and thereby shape the very structure of the universe as we perceive it. Gaining a better understanding of their existence and impact can reveal a great deal about how the cosmos has unfolded over billions of years. While we explore the intricate nature of black holes, it's also crucial to clear up some common fallacies about these celestial objects. Popular culture frequently depicts them as ravenous monsters that indiscriminately consume everything in their vicinity. However, the truth of their behavior is far more nuanced and scientifically interesting than these portrayals suggest. Throughout this exploration of black holes, we have barely begun to probe the depths of what is yet to be discovered. Each new finding prompts us to ask new questions, and every solution we find only reveals more pathways for our curiosity to follow. The quest for knowledge about black holes is, at its heart, a quest to understand our own position within the vastness of the cosmos. The birth of a black hole stands as one of the most spectacular events in the universe. But how do these enigmatic objects, which seem to defy our established physical laws, actually come into being? To find the answer, we need to examine the life cycle of truly massive stars, which are brilliant giants that can conclude their existence by collapsing into black holes. First, you can think of a star as being somewhat like a continuous hydrogen bomb explosion. Throughout most of its lifespan, it preserves a very fine equilibrium between the inward pull of gravity and the outward force of internal pressure created by nuclear fusion at its core. But the crucial question is what occurs when a star many times the size of our Sun finally depletes its nuclear fuel. When that moment arrives, the internal pressure is no longer sufficient to counteract gravity's relentless force, which then takes over and causes the star to undergo a catastrophic collapse. This implosion sets off a magnificent cosmic blast known as a supernova. an explosion so brilliant it can outshine millions of stars and remain visible from thousands of light-years away. Yet what is left behind at the center of this cataclysm can be even more extraordinary. If the mass of the leftover core is substantial enough, it will give rise to a black hole. In this transformation, the star's outer layers are violently expelled into space during the supernova, while the core continues to collapse in on itself. A core with enough mass will ultimately crush down into a point of infinite density called a singularity. It is at this precise instant that a black hole is born, a region of space-time with gravity so immense that nothing, not even light itself, can escape its grasp. Consider a dying star. At the end of its life, its own immense gravity becomes an unstoppable force, crushing it inward until a black hole is born. This process transforms the star into an entity with a gravitational pull so powerful, it fundamentally tests our comprehension of the universe. Yet not all black holes are created equal. Different varieties exist, with their formation being directly tied to the mass of the parent star. The kind known as stellar black holes originate from stars that are at least 3 times more massive than our Sun. But there are others that are vastly larger still, the supermassive black holes that reside at the centers of galaxies. How do these cosmic giants come into being? The full picture isn't entirely clear, but the prevailing belief is that they expand by consuming other black holes, or by steadily accumulating the gas and stars in their vicinity. The formation of any black hole also prompts fascinating questions about the life cycle of stars. When a massive star detonates as a supernova, it doesn't just leave behind a black hole. It also scatters heavy elements across the cosmos, providing the raw materials for new stars, planets, and perhaps even life. Doesn't it feel incredible to consider that black holes are in this way an essential component of the cosmic engine? Their very nature forces us to reconsider how we perceive space and time. When a star collapses into a black hole, it becomes more than just an object that can devour light. It actively warps the fabric of space-time surrounding it. This suggests that the laws of physics as we know them might not operate in the same manner in such extreme environments, which opens up profound implications for our understanding of reality. The concept of black hole creation serves as a powerful reminder that our universe is in a state of perpetual change. Stars are born, they live out their lives, and they die, sometimes creating black holes that can persist for millions or even billions of years. It's been demonstrated that supermassive black holes shape galactic dynamics, directly impacting star formation and the overall evolution of the galaxies they inhabit. These enigmatic objects are therefore not merely a final stage, but a vital part of the cosmos's life cycle. Ultimately, the formation of a black hole is a spectacle of nature that highlights just how little we truly grasp about the universe. Each new piece of information we gather about them seems to generate new questions, fueling our curiosity and driving further research. So when you find yourself gazing at the night sky, take a moment to wonder what tales are concealed within those distant points of light. Contemplate the black holes that may be hiding in the dark, patiently awaiting discovery. Black holes represent one of the most profound mysteries of the cosmos, and they are far from uniform. Did you know that, much like fingerprints, every class of black hole possesses unique traits that set it apart from the rest? Let's journey into this captivating realm to explore the different types of black holes that populate our universe. First up, we have stellar black holes, which are the most prevalent type and are formed from the death of colossal stars. When a star has burned through all its nuclear fuel, it can no longer withstand its own immense weight and begins to collapse. This catastrophic implosion triggers a brilliant explosion we call a supernova. If the core left behind after the blast has enough mass, it continues to collapse into a stellar black hole. Try to envision an object compressed so profoundly that its gravity creates an inescapable trap for anything that ventures too close. Now, let's turn our attention to supermassive black holes. These galactic titans can be found at the core of almost every major galaxy. Unlike their stellar cousins, supermassive black holes can possess masses millions or even billions of times greater than our Sun. Their origin is still a subject of intense debate, but some scientists theorize they formed from the mergers of smaller black holes or from the collapse of enormous gas clouds in the early universe. We also mustn't overlook the more elusive intermediate mass black holes. These objects occupy a mass range between their stellar and supermassive counterparts, but a clear consensus on their formation has yet to be reached. Some researchers propose they could be the result of several stellar black holes merging together, while an alternative theory suggests they might form in the dense cores of globular star clusters, making their existence a puzzle that scientists are actively working to solve. Each type of black hole exhibits its own distinct behavior, which makes studying them so compelling. Stellar black holes, for instance, might be relatively small, yet their gravitational force is unbelievably potent. When a star is reborn as a stellar black hole, its pull becomes so extreme that nothing, not even light itself, can break free from its grasp. On the other hand, supermassive black holes are so immense that their influence can extend across entire galactic systems, shaping them from afar. Some theories suggest that a supermassive black hole acts as the heart of its galaxy, raising fascinating questions about the relationship between these objects and the stars that surround them. As stars orbit this central mass, its gravity can actually influence the birth of new stars, establishing an incredible cosmic cycle of life and death. This just goes to show that sheer size isn't always the most important factor when it comes to cosmic influence. What makes black holes truly compelling is often how they engage with their surroundings. For example, stellar black holes have the ability to pull in and consume matter from stars in their vicinity. This act unleashes a tremendous surge of energy in the form of radiation that we can detect from our planet. It gives the impression that these cosmic objects are publicly feasting, allowing us to witness the shimmering spectacle of their meal. Astronomers are also deeply intrigued by intermediate mass black holes, even though they are observed less frequently. The reason for this fascination is that figuring out how they come into being could provide vital hints about the origins of supermassive black holes. If we can solve the puzzle of these mid-sized objects, we might get much closer to understanding the developmental history of both galaxies and the entire cosmos. It's fascinating to consider the ways these different classes of black holes influence one another and the space around them. You can picture a grand celestial ballet where each type performs a unique part, from a compact stellar black hole consuming a neighboring star to a colossal supermassive black hole orchestrating the movements of thousands of stars. Each contributes its own distinct flair to the cosmic performance. As our comprehension of black holes deepens, we find ourselves unlocking not just their own enigmas, but the secrets of the universe at large. Every new piece of information moves us closer to resolving fundamental questions about the nature of existence. How immense is the cosmos really? What other puzzles are still waiting for us to discover? Black holes serve as gateways to a universe of untold possibilities, and each variety is a piece of the puzzle. So, as our exploration of these captivating phenomena continues, it's important to recognize that every black hole, whether stellar, supermassive, or intermediate, is a vital chapter in the cosmic narrative. They beckon us to gaze upward and challenge our current understanding of the universe, compelling us to push beyond the limits of what is known. On this path of discovery, each type of black hole acts as a guidepost, lighting the way toward the future of astrophysics and cosmology. What exactly is a black hole? While the question might appear to have a straightforward answer, these objects are in fact among the most thrilling and enigmatic phenomena in the cosmos. They represent areas in space where the force of gravity is so powerful that nothing, not even light, can break free from its grip. But how can this be? To grasp this concept, you first need to delve into what a black hole fundamentally is. A black hole is born when a gargantuan star runs out of nuclear fuel and implodes under its own immense gravity. You can visualize this by imagining a massive bowling ball dropped onto a trampoline. As the ball descends, it creates a deep depression, and if the trampoline lacks the strength to support it, the ball will collapse through entirely. Similarly, a star transforms into a black hole when all its mass is compressed into an infinitesimally small space, producing an almost inconceivable distortion in spacetime. The essence of understanding a black hole is grasping its event horizon. You might be wondering what that is. Picture it as an invisible threshold, a boundary that signifies the ultimate point of no return. After you've crossed this line, there is simply no turning back. It's akin to navigating a labyrinth where every step deeper makes finding an exit progressively more impossible. But what would happen if you were to venture too close to a black hole? The result might surprise you. As you draw nearer to the event horizon, the gravitational pull becomes utterly overpowering. This is where the idea of spaghettification becomes relevant. Imagine your body being stretched out like a noodle. This occurs because the gravitational force is significantly stronger on the parts of you closer to the black hole than on the parts farther away. Consequently, any object that strays too near is elongated and pulled apart in a process that is as fascinating as it is horrifying. Another captivating idea is the singularity, located at the very heart of a black hole. In this spot, the entire mass of the collapsed star is squeezed into a point of infinite density and zero volume. In this domain, the laws of physics as we understand them completely break down, presenting a profound challenge to our comprehension of the universe. What this signifies for science is that, for all our progress, there are still deep mysteries that we have yet to solve. Beyond its effect on nearby matter, a black hole's gravity also warps time itself. Albert Einstein's theory of relativity demonstrates that time is not a universal constant. Instead, it flexes in response to gravity. Were you to find yourself in a region of incredibly intense gravity, like that near a black hole, your experience of time would be markedly different from that of the rest of the universe. This opens up some incredible possibilities. Could journeying through time be as simple as getting near a black hole? However, gravity and time aren't the only enthralling features of black holes. You also have the phenomenon of tidal forces, which function much like the moon's gravitational pull creates tides on Earth. A black hole can impose similar tidal forces on objects in its proximity. If a star ventures too close, these forces can tear it to shreds, creating a cosmic display of unbelievable scale. Just try to picture what observing such an event from a safe distance would be like. Over the years, the investigation of black holes has spurred remarkable breakthroughs in the field of astrophysics. The methods scientists have used to infer the presence of these objects are truly extraordinary. By relying on indirect observations and analyzing their impact on their cosmic environment, astronomers have successfully charted the universe, including the locations of these cryptic phenomena. The significance of black holes goes far beyond their formation and mere presence. These objects are integral to the very architecture of the cosmos. It's now established that supermassive black holes, which reside at the centers of most galaxies, can heavily influence how those galaxies form and evolve over time. It's remarkable to consider how such a compact object, relative to the immensity of space, can wield such a profound impact. Our innate human curiosity pushes us to wonder what else might exist beyond black holes. Given how intriguing these objects are, could they perhaps be portals to other universes? While this notion veers more toward science fiction, the concept of wormholes, theoretical tunnels that could bridge distant points in spacetime, has certainly ignited the imagination of many. Within the captivating domain of astrophysics, black holes represent phenomena that stretch the very limits of what we comprehend about physics. Have you ever considered how a celestial object can fundamentally warp the fabric of space and time around itself? When I discuss black holes, I'm talking about specific areas in space where the pull of gravity is so immense that absolutely nothing, not even light, can break free from its grasp, forcing us to reevaluate our most fundamental beliefs about the cosmos. At the very core of a black hole lies a singularity, a concept that might initially seem difficult to grasp, but is essential for understanding their true nature. A singularity is effectively the heart of a black hole, a point where the force of gravity intensifies to infinity and the physical laws we rely on appear to completely break down. But how can such a thing be possible? To make this clearer, let's draw a parallel to an ordinary experience. Picture a car accelerating along a perfectly straight road. As its velocity climbs, it almost seems to become lighter. In the vicinity of a black hole, gravity behaves with a similar escalating effect. As you draw nearer, its pull grows to such a degree that you would feel progressively heavier, until this force becomes so overwhelming that nothing can withstand it, light included. This intense gravitational force compels us to question our most basic ideas about how the universe operates. Now, let's explore the implications this has for matter itself. Deep inside a black hole, the singularity is so incredibly dense that the entire mass of the original collapsed star is crushed into a virtually dimensionless space. This creates a point of infinite density where our conventional understanding of space and time is radically transformed. We find ourselves confronting a profound enigma, as our current physical laws are incapable of describing what unfolds in such an extreme environment. Scientists have made numerous attempts to create models of the events inside a singularity, but they consistently run into a conceptual dead end, much like trying to assemble a puzzle with crucial pieces missing. While Einstein's general theory of relativity provides an excellent framework for gravity's behavior across the universe, it falters when applied to the singularity. It seems a new theory is required, one that successfully merges relativity with quantum mechanics. But such theories are still in the developmental stages, keeping physicists on a relentless quest for answers. Moreover, the singularity brings forth deep philosophical inquiries. What is the ultimate fate of the information that is pulled into a black hole? Does it vanish without a trace, or is there some mechanism by which it could be recovered? This conundrum, famously known as the black hole information paradox, has sparked vigorous debates among both physicists and philosophers, challenging our very concepts of identity and memory when faced with the idea of them disappearing into a cosmic void. One of the most fascinating qualities of singularities is their profound relationship with time. Within the confines of a black hole, time does not behave in the way we experience it. Close to the singularity, time might grind to a halt or operate in ways that are entirely alien to our daily lives. This leads us to contemplate the deep and still poorly understood connections between gravity and time, raising the possibility that black holes are not merely traps for matter, but for time itself. Black holes and their singularities also compel us to reflect on the fundamental structure of our universe. The very existence of these points of infinite density suggests that the vastness of space may hold other astonishing surprises. it's quite possible that the true nature of gravity and matter is far more complex than we can currently conceive. This inherent curiosity is what propels us to continue exploring and questioning, as each new discovery seems to simply unlock a door to more profound questions. When you truly ponder the concept of a singularity, it is impossible not to experience a profound sense of wonder and reverence. The notion that there are locations in the cosmos where the established rules of physics no longer hold serves as a powerful reminder of how much we have yet to learn. Simultaneously, it acts as a powerful source of inspiration, urging us to persist in our journey of exploration and discovery, because science has always progressed through relentless curiosity and the brave pursuit of the unknown. Even so, whether these phenomena are truly real continues to be a topic of intense study and discussion. Ultimately, black holes are vastly more significant than mere dark voids in the night sky. They serve as portals into the universe's deepest secrets, compelling us to reconsider everything we thought we knew about gravity, time, and the very fabric of existence. The next time your gaze turns toward the heavens, I want you to remember that those immense, dark expanses harbor truths we are still striving to comprehend. The search for answers about singularities may very well guide us to entirely new frontiers in both science and philosophy. For the time being, however, the enigma of the singularity serves as a potent reminder that, within the grand design of the universe, there will invariably be more to uncover. It stands as a symbol of our collective thirst for knowledge, pushing us to persistently ask questions and hunt for answers, no matter how formidable the challenges may seem. Perhaps, at some point in our future, we will finally decode the secrets of the singularity and grasp the role it plays within the immense cosmic tapestry. Until that day arrives, it will persist as one of the most profound mysteries of modern physics. Exploring black holes not only furnishes us with answers, but also inspires us to keep posing new questions and learning about our unique position in the cosmos. The great adventure of discovering the unknown goes on, and black holes are merely the prelude to an extraordinary voyage across the universe. To appreciate how a black hole's gravity warps our understanding of space and time, you first need to comprehend the event horizon. This unseen demarcation represents the ultimate threshold, a boundary from which escape is impossible. Think of it like diving into a pool. There's a specific moment when turning back to the edge is no longer an option. The event horizon is a cosmic version of this, representing the exact location where the fundamental laws of physics are radically altered. Albert Einstein's theory of relativity provides a revolutionary perspective on gravity. Rather than seeing it as a simple, attractive force, Einstein revealed that gravity is actually the curvature of spacetime itself. To visualize this, picture a flat sheet with a heavy bowling ball placed in its center, causing the surface to sag. If you then roll marbles nearby, they will naturally move toward the depression created by the ball, which is precisely how immense objects like black holes distort the fabric of spacetime, drawing everything around them into their gravitational well. So how does time fit into this picture? Gravity's influence extends beyond space, profoundly altering our experience of time. In the vicinity of a black hole, time itself becomes elastic, meaning the nearer you get to its immense gravity, the more slowly time flows for you relative to a distant observer. Consider a scenario where a friend journeys close to a black hole while you stay on Earth. Upon their return, they might discover that decades have passed for you, even though only a few days elapsed for them. This extraordinary effect, known as time dilation, stands as one of relativity's most mind-bending paradoxes. While the notion of gravity warping time may sound like a concept from science fiction, it is a proven scientific fact. For instance, astronauts aboard the International Space Station experience a minute difference in the passage of time, because they are in a weaker gravitational field than we are on the surface. Even though the effect is too small for us to notice, their clocks do indeed tick at a slightly different rate than those on the ground, confirming this strange reality. A black hole's gravity also exerts a devastating physical impact on anything that ventures too close, a phenomenon driven by what are known as tidal forces. Picture yourself on a boat being tossed by waves, and then imagine a colossal wave capable of tearing your vessel apart. An object approaching a black hole faces a similar fate, as the gravitational pull on the side mirror of the black hole is vastly stronger than on the far side. This differential force stretches the object until it is torn to pieces in a process aptly named spaghettification. The more we learn about black holes, the more they compel us to question our fundamental view of the cosmos, forcing a re-evaluation of the connection between gravity and time. These enigmatic objects challenge our intuition, but also unveil profound truths about reality, which is the very beauty of physics. Furthermore, studying black holes reveals their link to other cosmic events. The collision of two black holes, for instance, generates gravitational waves, ripples in spacetime, that offer direct insights into gravity's true nature and open new avenues for cosmic exploration. Our innate curiosity is the engine that drives our quest to understand the workings of the universe. If you've ever found yourself pondering what might exist beyond a black hole, you're tapping into the same impulse that pushes science to its frontiers. While purely speculative, some modern theories even propose that black holes might act as portals to other universes, a concept that challenges us to reconsider not just space and time, but the fundamental nature of reality itself. Each new finding about black holes inches us closer to grasping the universe's intricate design, yet it also presents us with profound and seemingly unanswerable questions. What secrets are hidden within a black hole's depths, and what is the true meaning of the singularity at its heart? The pursuit of these answers is an expedition as exhilarating and vast as the cosmos we seek to understand. The concepts of relativity and gravity are merely pieces of a much larger puzzle, as the interaction of black holes with spacetime demands that we question our assumptions and embrace the unknown. The narrative of black holes ultimately reflects our own journey. It highlights that despite our scale in this immense universe, it is our relentless curiosity that defines our humanity. In investigating these cosmic mysteries, we are really investigating ourselves and our position in the cosmos, constantly reminded that every discovery only leads to deeper questions, pushing the boundaries of human thought ever outward. Black holes are among the most captivating and formidable phenomena in the cosmos, and one of their most compelling features is the tidal effect they produce. To grasp what this means, consider the familiar ocean tides on Earth, which are a direct result of the gravitational pull from the moon and sun. When one celestial body's gravity acts upon another, it can create a deforming force. Now, magnify that force to the extreme intensity of a black hole, whose immense gravity isn't uniform but varies dramatically with distance, profoundly affecting anything in its vicinity. As any object draws near a black hole, the gravitational force on its nearest point becomes intensely stronger than on its furthest point, a principle we call the tidal effect. Just consider what this means for a planet that ventures too close. The immense gravitational pull on the side facing the black hole, contrasted with the much weaker pull on the far side, would create a catastrophic imbalance, stretching the planet and potentially ripping it to shreds in a process aptly named spaghettification. Now let's picture a spaceship on a journey near a black hole. At first, from a safe distance, you could marvel at the sight of this cosmic titan. However, the situation would grow increasingly precarious as you drew nearer. The ship's bow, being closer to the black hole, would be tugged forward with far greater force than its stern, elongating the entire vessel as if it were a strand of spaghetti. While this is a dramatic example, it provides a perfect visualization of the tidal effect at work. You might wonder why understanding this phenomenon is so crucial, and the reason is straightforward. Tidal effects are not exclusive to black holes. You can see them with other celestial objects, like stars and planets. The moon's gravitational pull, for instance, creates the tides in our oceans. But if a planet were in proximity to a black hole, these same forces would be catastrophically amplified. And some theories even propose that the presence of a black hole in a star system could have unforeseen consequences for the development of life. These tidal forces also play a role in shaping large-scale cosmic structures. As a black hole pulls in matter from its environment, this material often settles into a rotating accretion disk. The black hole's gravity is so powerful that it churns this gas and dust into a swirling vortex, heating it to extreme temperatures until it radiates with incredible brilliance. This is how quasars are formed, some of the most luminous objects in the cosmos, and a clear testament to a black hole's profound impact on its galactic neighborhood. Considering the way tidal effects work on orbiting bodies, you can envision a solar system centered not on a star, but on a supermassive black hole. The stars in such a system would be subject to both the black hole's overall gravity and its potent tidal forces. These disruptive forces could warp their orbital paths into highly elongated ellipses, or in some cases, even fling them out of the system entirely. The narrative gets even more compelling when you scale this up to the galactic level. It's widely thought that supermassive black holes anchor the centers of most galaxies, with their immense gravity guiding galactic formation and evolution. These powerful gravitational interactions can drive entire galaxies to merge, reshaping the destiny of countless billions of stars. It's truly mind-boggling to realize that a single object can command the structure of an entire galaxy. So, what becomes of objects poised at the very brink of the event horizon, the point of no return from which nothing escapes? At this boundary, the tidal effect reaches its most extreme. Anything crossing this threshold is doomed, entering a realm where gravity is so overpowering that it warps the very fabric of space and time. An observer watching from afar might see only a moment pass, but for the object falling in, that same moment could stretch into an eternity. Ultimately, the tidal effect is more than just a captivating cosmic event. It's essential for comprehending how these universal behemoths engage with their environment. From distorting celestial bodies to steering the development of entire galaxies, these gravitational tides are a constant reminder of their immense power. So, the next time you picture a black hole, think of it less as a mere devourer of light, and more as a cosmic architect, molding the universe around it. With every new finding, we peel back another layer of the enigma surrounding black holes and their function in the cosmos. Who can say what other truths they hold, waiting to be uncovered as our exploration continues? Each breakthrough holds the potential to revolutionize our grasp of gravity, time, and our own place within this immense and mystifying universe. But have you ever considered that black holes might not only consume matter, but also radiate something truly remarkable? This is the concept of Hawking radiation, a captivating idea that challenges our fundamental understanding of these cosmic enigmas. You see, we typically think of a black hole as a cosmic vacuum, with gravity so powerful that even light cannot break free. But what if I proposed that, against all odds, these impenetrable objects have a way of leaking energy back into space? This is the revolutionary idea put forward by the theoretical physicist Stephen Hawking. He theorized that, because of quantum effects, black holes might not last forever. Near the event horizon, the constant fluctuation of the quantum vacuum causes pairs of virtual particles to pop into and out of existence. Occasionally, one particle from a pair falls into the black hole while the other escapes, carrying a tiny amount of energy with it. This escaping energy is what we call Hawking radiation. The consequence of this process for the black hole is profound. By radiating energy away, it simultaneously loses mass. That's correct. This means black holes can effectively shrink over time. You can think of it as a gradual weight loss program. If this emission continues for a sufficiently long period, the black hole could eventually evaporate entirely. This concept that black holes may have a finite lifespan is truly astounding, and has become a central topic of intense debate and research within the scientific community, directly opposing the traditional view of them as eternal cosmic fixtures. Even though direct observation of this radiation has eluded us, its confirmation would have transformative consequences for how we comprehend physics and the universe itself. Imagine if black holes are not merely cosmic traps for matter, but are instead portals to a deeper understanding of the relationship between matter and energy. Hawking radiation also introduces fascinating puzzles concerning information, which, according to quantum physics, can never be truly destroyed. This leads to a profound conflict. If a black hole completely evaporates, what happens to the information about everything it ever consumed? This very question, famously known as the black hole information paradox, has ignited fierce discussions among physicists and given rise to novel theories about the fundamental nature of our universe. One compelling idea suggests that the information might not be lost at all, but could instead be encoded within the Hawking radiation that escapes. The notion that information could break free from a black hole's grasp fundamentally challenges our current models of physics, and this remains a vibrant field of ongoing research. Furthermore, the existence of Hawking radiation forces you to consider the final destiny of the cosmos. If even black holes are transient and destined to evaporate over immense timescales, what does that imply for the long-term structure of everything? It suggests a possible future where the universe dissolves into a vast, featureless ocean of particles, an endless expanse of diffuse energy in perpetual motion. As our exploration of Hawking radiation deepens, a whole new realm of possibilities unfolds before us. The concept that black holes could be sources of energy and therefore not absolutely black compels you to reconsider them in an entirely new light. Is it conceivable that they could one day serve as power sources, waiting for a civilization advanced enough to tap into their energy? Hawking radiation represents just one of the many mesmerizing aspects of these cosmic enigmas, reminding us that science is a continuously evolving process, where each new insight brings us closer to solving the universe's greatest puzzles. As we persist in our scientific journey, the potential for groundbreaking revelations about black holes and their radiant properties fuels our desire to keep searching. Ultimately, Hawking radiation is a testament to humanity's intrinsic curiosity and our relentless drive to make sense of the unknown. Every question you and I pose about the cosmos inches us closer to the truth of our own existence. So, the next time you gaze up at the night sky, consider that within the profound darkness of space, there may be more than what we can see, perhaps even a hidden light that could illuminate our entire cosmic perspective. Within the imaginative landscape of science fiction, you often encounter wormholes, depicted as mysterious gateways connecting disparate points in space, and sometimes even time. But what exactly are these incredible phenomena? To grasp the concept, you must first remember that black holes are cosmic regions with gravity so intense that nothing, including light itself, can escape their grasp. Now, picture that deep within a black hole's core, its singularity, lies a passage that forms a tunnel to another region of the universe. This is the very essence of a wormhole, a theoretical shortcut through the fabric of spacetime. To make this clearer, consider a simple analogy. Imagine you have a sheet of paper that you fold in half. If you were to poke a hole through the center of the folded sheet, that opening would act as a bridge, directly linking two points that are otherwise far apart on the paper's surface. In theory, a wormhole operates similarly, serving as a conduit that connects two separate locations in the cosmos, allowing for travel that bypasses our conventional understanding of distance. The question of how such a wormhole might form brings us to the intricate interplay of gravity and relativity. Albert Einstein's general theory of relativity describes space and time as being woven together into a single continuum known as spacetime. It is within extreme distortions of this fabric, like those found around a black hole, that these cosmic connections might theoretically emerge. But as for whether they actually exist, scientists are still investigating. While the theory allows for them, we have yet to uncover any direct evidence confirming that wormholes are real. This naturally leads to another captivating question. Could we ever travel through a wormhole? The answer is far from straightforward. Most theoretical models indicate that, even if they did exist, these cosmic tunnels would likely be incredibly unstable, collapsing in on themselves before anything could successfully pass through. You can imagine the terrifying prospect of attempting to navigate a tunnel that is actively disintegrating all around you. Let's explore the idea that wormholes might be more than just a theoretical curiosity. Some scientists speculate that they could one day be utilized for transportation, enabling astronauts to cross immense cosmic distances in the blink of an eye. This, however, raises a host of new questions. If we were to find one, how could we possibly determine if it was safe to enter? Pondering these issues forces you to confront the very limits of our current grasp of the universe and the laws of physics. The concept of wormholes has also thoroughly captivated the imaginations of storytellers. You can see this in countless films and novels that explore travel through these cosmic passages, where characters leap between worlds, defying the normal constraints of space and time. But is there any scientific foundation for these narratives? While science fiction certainly takes creative license, the idea is rooted in genuine scientific principles, lending an exciting element of plausibility to these tales. One of the most thrilling aspects is the link between wormholes and quantum gravity, a theoretical field attempting to reconcile general relativity with quantum mechanics. Theorists propose that a future unified theory might finally help us understand how wormholes function. It's as if these cosmic tunnels are waiting just beyond the frontier of our knowledge, poised to give up their secrets as our science advances. This leads some to wonder, could wormholes also permit time travel? If they can truly connect 2 points in both space and time, it raises the mind-bending possibility of journeys into the past or the future. While the notion of wormholes certainly fires up the imagination, it also presents us with profound ethical and philosophical challenges. If you could actually alter the past, consider the cascade of effects that would ripple through to your present reality. The concept of time paradoxes is a staple of science fiction, and thinking through these outcomes is essential for grasping our own position in the cosmos. The idea of wormholes also forces you to contemplate the function of negative energy, a theoretical substance possibly required to prop a wormhole open. The very existence of this energy remains a topic of intense debate among physicists. Should it be proven real, it could unlock entirely new paradigms for comprehending the universe, inviting you to picture a cosmic passageway sustained by this thrilling yet intricate force. Amid all this excitement, it's crucial to remember that wormholes are still a compelling concept far from being proven. Science is in a state of constant evolution, meaning what seems impossible to you today could very well be tomorrow's reality. The insatiable curiosity and drive to explore the unknown are what fuel scientific progress, with every new insight moving us closer to solving the universe's greatest riddles. The very concept of wormholes encourages you to pause and reflect on your own existence within the immense universe we call home. You are an integral part of a cosmos teeming with marvels and mysteries. Every question you pose about space and time brings you nearer to understanding your specific place within this grand design, making the study of wormholes just one leg of an unending quest for knowledge. So, as you continue to look up at the stars, keep in mind that each theory, every discovery, and all the questions you ask represent a step forward. Science is a continuous journey, with wormholes serving as just one of many fascinating stops on the path to the unknown. It's entirely possible that as our understanding of the universe deepens, we will find that wormholes are not mere fictions, but tangible realities awaiting us in the vastness of space. Black holes are celestial phenomena that appear to operate outside the logical framework of how you perceive time. But to grasp what actually occurs with time as you near one of these enigmatic objects, it helps to envision time as a river. In your daily life, this river's flow is steady and predictable. Yet in the vicinity of a black hole, its currents are twisted in truly astounding ways. Picture yourself on a boat floating down this river of time, when you suddenly come upon a massive whirlpool that represents the black hole's gravitational field. As you drift closer, you can feel the current accelerating violently around you. While you are technically in the same flow of time, the environment around you undergoes a dramatic transformation. Because a black hole's gravity is so powerful, it fundamentally alters your experience of time itself. For an observer watching from a great distance, time would appear to slow down for anyone approaching the event horizon, that is, the point of no return beyond which nothing can be seen. You can imagine being inside that whirlpool, where time passes differently for you than for those far away. For the person nearing the black hole, the passage of time might feel completely normal, but to a faraway observer, that individual would seem to move at an ever-decreasing pace, as if caught in a state of suspended animation. This effect is famously known as time dilation, and it stands as one of the most remarkable predictions of Einstein's theory of relativity. The reason this occurs is rooted in the way gravity interacts with both space and time. Across the universe, gravity does more than just pull on objects. It actually bends the very fabric of spacetime. The more condensed a mass is, like that of a black hole, the more extreme this warping becomes, causing time itself to stretch and distort for you or anyone else nearby. This phenomenon isn't merely theoretical. It's been validated through experiments using hyper-accurate atomic clocks. When these clocks are positioned at higher altitudes, like on a mountaintop where gravity's pull is slightly weaker, they run fractionally faster than identical clocks at sea level. Now, imagine how dramatic that time difference would become near a black hole, reminding you that time is not a universal constant, but a variable that can be manipulated by gravity. What then are the implications of this for time travel? If you could somehow approach a black hole, withstand its forces, and return home, you might discover that centuries had passed on Earth while you only experienced a few minutes. This kind of scenario is frequently explored in science fiction, but the reality is that the physical and technological hurdles of getting close to a black hole are truly staggering. Even so, considering the relationship between black holes and time compels you to reflect on your own life. We often get caught up in tracking every minute and second. But what if time isn't as rigid and linear as you assume? Black holes serve as a cosmic invitation to question your everyday perception of time and to envision a universe where temporal experiences can be radically different. Furthermore, the study of black holes and their temporal effects opens pathways to entirely new theories about the cosmos. Some scientists speculate about the possibility of traveling through time via wormholes, which are hypothetical tunnels through spacetime. While these concepts are still speculative, they demonstrate that modern physics remains a vibrant field for both imagination and scientific inquiry. Ultimately, black holes are more than just astronomical bodies. They are gateways to profound questions about your existence and your comprehension of the universe. They confront you with the fact that there is so much left to discover and understand. With every new insight we gain about black holes, we move a little closer to deciphering the fundamental mysteries of time and space. So the next time you find yourself thinking about black holes, remember that they represent more than just strange cosmic objects. They are powerful reminders that your current understanding of time and space is far from complete, and that the universe holds far more wonders than you can possibly imagine. The expedition into the unknown presses onward, and every new solution unlocks further avenues for inquiry and awe. Trying to observe black holes is much like being a detective, piecing together evidence at a cosmic crime scene. Consider the challenge you'd face in solving a grand mystery where the central object, the black hole itself, remains utterly invisible. So how do you confirm the existence of something that neither emits its own light nor reflects any light around it? The solution is found by studying its effects on nearby matter. When a star drifts too close to a black hole, the immense gravitational pull can violently rip it apart, unleashing a brilliant spectacle of light and energy that we can detect as radiation. This event, known as accretion, serves as the primary method for observing these enigmatic cosmic bodies. Astronomers employ powerful telescopes sensitive to different light wavelengths, such as X-rays and radio waves, to actually see the telltale signs of black holes. As material spirals inward, it becomes incredibly hot and radiates energy at these specific wavelengths, making the invisible visible. The Chandra X-ray Observatory, for instance, has been instrumental in pinpointing stellar mass black holes within our own galaxy by detecting these high-energy emissions. This instrument gives us a perspective similar to a microscope, allowing us to peer into the deepest shadows of the cosmos. But how can we be absolutely certain that a black hole is the culprit? One of the most compelling methods involves monitoring stars that appear to be orbiting an empty point in space. When astronomers notice a star exhibiting an unusual trajectory, it strongly suggests a black hole is exerting its influence nearby. Imagine you're at a playground, and you see a swing moving back and forth as if propelled by someone. Yet no person is visible. You'd logically conclude an unseen force is at work. And a star's behavior can similarly point to the presence of a black hole. This phenomenon is even more pronounced with the supermassive black holes residing at the heart of most galaxies, including our own Milky Way. By tracking the orbits of stars in the galactic center, scientists can precisely calculate the black hole's mass, even without ever seeing the object itself, much like determining the weight of an elephant in a pitch-black room, simply by analyzing the sounds and vibrations it creates as it moves. The ability to detect gravitational waves has completely transformed how we observe the universe. These are minuscule disturbances in the fabric of space-time, generated by cataclysmic events like the merging of two black holes. When these cosmic titans collide, They send out gravitational waves that propagate across the cosmos. With advanced observatories like the Laser Interferometer Gravitational Wave Observatory, or LIGO, scientists can now effectively listen to these distant cosmic collisions. It is analogous to possessing a colossal microphone capable of catching the faint echo of a shout from millions of light years away. Thanks to technological progress, it has even become feasible to directly photograph a black hole's silhouette. In 2019, the Event Horizon Telescope collaboration achieved a monumental feat by capturing the first-ever image of the supermassive black hole at the center of the M87 galaxy. Though the image appears fuzzy, its acquisition marked a pivotal moment in scientific history. This achievement can be likened to capturing the first photograph of a mythical creature that was previously known only through stories and folklore. Astronomers also analyze relativistic jets, which are powerful streams of particles ejected from the vicinity of some black holes. These jets race through space at nearly the speed of light and are clearly visible in the radio wave spectrum. Observing them provides crucial data about the black hole's activity and its immediate environment. It's comparable to spotting the exhaust trail from a rocket launched into the sky, which signals the operation of a powerful engine hidden from direct view. Radio telescopes are indispensable instruments in this quest, allowing scientists to map the area surrounding a black hole by detecting the radio waves emitted from the swirling material. This technique is similar to using radar to pinpoint a submarine concealed deep beneath the ocean's surface. The submarine itself is out of sight, but the radar waves it reflects give away its exact location. As researchers continue to innovate, our methods for detecting black holes grow increasingly precise and powerful. Enhancements in telescope technology, the application of artificial intelligence to analyze vast data sets, and extensive international collaborations are all contributing to our evolving comprehension of the universe. This is a truly collective endeavor, much like a symphony orchestra where every musician's part is essential to producing the final, magnificent cosmic composition. This work is not only scientifically captivating, but also encourages us to contemplate our own place within the cosmos. Each new insight we gain into these phenomena brings us a step closer to grasping the very limits of space and time. What profound secrets might they unveil in the years to come? This single question continues to fuel our scientific curiosity and our drive for exploration. Every black hole we identify serves as a portal into the unknown and represents a new chapter in the grand story of the universe. As we refine our ability to study these perplexing objects, we deepen our understanding of gravity, dark matter, and the intricate ways everything fits together in the cosmic puzzle. Ultimately, the hunt for black holes is a search for understanding, a mission to comprehend our own position within this immense and still largely mysterious cosmos. Therefore, as we venture deeper into this field of study, we are not merely looking into a void. Instead, we are immersing ourselves in a cosmic ballet of light and shadow, where every discovery compels us to redefine our limits and push the frontiers of what we know. Investigating these cosmic puzzles is a journey not just across space, but through time, history, and the fundamental nature of reality itself. Have you ever stopped to think about how black holes actually shape the galaxies we see? These enigmatic entities are far more than just cosmic vacuum cleaners. They are foundational to the very architecture of the universe. Picture every galaxy as a sprawling metropolis, with a supermassive black hole at its core acting as a kind of powerful gravitational anchor. Without that central influence, the entire process of how galaxies form and evolve would be radically different, because the existence of black holes is intrinsically tied to the birth of galaxies themselves. During the formation of a galaxy, vast quantities of matter pulled together under the relentless force of gravity. As this material gathers, it can give rise to black holes at the galactic core. But what if I were to tell you that these same black holes can actually facilitate the creation of the stars and other celestial objects that circle them? It's true. Their powerful gravity orchestrates the motion of stars, almost like a conductor leading a grand cosmic symphony. The relationship between black holes and galaxies is an incredible, self-perpetuating cycle. As a supermassive black hole expands, it is able to draw even more matter toward it. This activity not only nourishes the black hole, but can also trigger the birth of new stars in its immediate surroundings. You might picture a black hole as a kind of celestial gardener, simultaneously consuming its environment while cultivating the growth of new stellar bodies, which is one way to grasp how these cosmic behemoths shape their domains. But their influence doesn't stop there. The very presence of a black hole can determine the physical structure of its host galaxy. Galaxies that harbor supermassive black holes at their centers tend to be larger and more structurally intricate. The black hole's gravitational field can dictate the arrangement of stars, forging denser formations, and sometimes even warping the galaxy's overall form. Think of it like gravity determining the layout of a city's architecture. A similar dynamic unfolds in the cosmos. When you consider the wider effect of black holes across the entire universe, the picture becomes even more fascinating. The continuous formation of black holes seems to create a type of cosmic balance. The influence of these gravitational titans helps to impose order on what might otherwise be cosmic chaos. In a way, they function as custodians of the universe's architecture, helping to regulate the distribution of galaxies throughout space. What then occurs when two black holes collide? These encounters can result in breathtaking mergers that unleash staggering amounts of energy as gravitational waves. These waves propagate through the fabric of spacetime like ripples from a cosmic detonation. So, each time you hear about the merger of black holes, you are learning about an event that is actively reshaping the universe itself. Turning to the subject of energy, black holes are also deeply connected to some of the broadest ideas in cosmology. Their very existence poses profound questions about dark matter and dark energy, which remain two of the greatest puzzles in the universe. It's possible that black holes hold the secret to understanding how matter behaves on the largest scales and how it drives the expansion of the cosmos. You can think of these enigmatic objects as a vital part of the solution to how everything truly operates. The dynamic interplay between black holes and galaxies isn't just a phenomenon for us to observe. It also carries deep philosophical weight. Contemplating the sheer scale of the universe and the power these giants wield over everything we can see forces you to ask, how much do we genuinely comprehend about our own position in the cosmos? Every black hole we investigate moves us a step closer to solving the grand puzzle of existence. Furthermore, black holes provide profound lessons about the nature of time and space. Their immense gravity has the power to warp how we perceive time, compelling us to reflect on the fundamentals of our own reality. What is the true meaning of time in a universe where it can be so radically distorted by a black hole? This intimate connection between gravity and time is a subject that beckons us to explore the very fabric of our world. To summarize, black holes are so much more than simple cosmic devourers. They are central characters in the story of the universe, sculpting galaxies, guiding the dance of stars, and inspiring fundamental questions about the essence of space and time. Every new discovery about them provides a fresh lens through which to view our role in the limitless expanse of the cosmos. And as our exploration presses forward, we continue to piece together the universe's narrative, a story in which black holes are unquestionably major protagonists. Within the immense field of astrophysics, black holes have thoroughly captured the minds of both scientists and the public. Yet, they are frequently shrouded in myths and mistaken ideas that can easily mislead anyone who hears about them. One of the questions I hear most often is whether they truly consume everything that ventures too close. The reality is far more nuanced than that simple picture suggests. The truth is, black holes do not function like cosmic vacuum cleaners, indiscriminately pulling in everything in their vicinity. Their gravitational influence is only overwhelming at a close range. If you were piloting a spacecraft at a secure distance, you could observe one without any danger at all. This helps to dispel the image of them as insatiable predators roaming through space. Another prevalent misconception is the idea that all black holes across the universe are fundamentally the same. But are you aware that there are multiple categories of black holes? They range from stellar black holes, born from the collapse of gigantic stars, to the supermassive black holes residing at the heart of galaxies, each with its own unique properties. You could visualize a stellar black hole as a formidable beast, yet it pales in comparison to the colossal supermassive black hole that reigns over its entire galaxy. Their diversity is truly remarkable. Popular culture has also popularized the notion of black holes as gateways to other dimensions. Is this a genuine scientific possibility, or is it purely the stuff of fiction? While the theory of wormholes does entertain this concept, there is currently no substantial evidence to support the idea that they could serve as actual interstellar doorways. Still, who can blame you for dreaming about the potential for travel across space and time? And surely you've heard the famous term, singularity. This word describes a theoretical point where the laws of physics as we understand them completely break down. The singularity inside a black hole generates fascinating questions about the fundamental structure of space and time. We don't know for certain what happens at this point, and it is precisely this deep uncertainty that makes the study of black holes so utterly captivating. Ultimately, the popular image of black holes as all-consuming monsters is a significant departure from the scientific reality. In fact, the renowned physicist Stephen Hawking proposed the famous concept of Hawking radiation, which suggests that black holes might actually evaporate over immense timescales. This idea forces you to wonder if black holes might not be eternal after all. It's an unexpected twist that challenges our conventional views and encourages us to consider their life and death in ways we never thought possible. Another frequently misunderstood concept is the way black holes can influence time. You have surely noticed how quickly hours pass when you're absorbed in something enjoyable. Now, try to picture yourself in proximity to a black hole, where time operates very differently from our experience on Earth. This phenomenon occurs because the object's immense gravity literally bends the fabric of spacetime, meaning a traveler near a black hole would perceive time passing at a completely different rate than an observer situated far away. Stellar black holes, which are the remnants of collapsed massive stars, are captivating subjects on their own. But I wonder if you've considered what unfolds when two of these objects collide. Such an encounter can result in a merger that forges an even more massive black hole, similar to two separate worlds crashing together to create a single, more powerful entity. This event is not just spectacular, it also unleashes gravitational waves that our scientists can detect here on Earth. The popular image of a black hole as a ravenous monster captures only a tiny fraction of its true complexity. These objects are often wrongly linked with nothing but chaos and destruction. But in truth, they are fundamental to maintaining balance in the universe. It's plausible that without them, galaxies would not take on the shapes they do. In this light, black holes act more like cosmic gardeners, meticulously sculpting the vast landscapes of space. The possibility that black holes could affect dark energy is also a topic of intense scientific debate. Is it conceivable that these phenomena are connected to the enigmatic force that appears to be driving the accelerating expansion of our universe? Current research is dedicated to uncovering this potential link, which could dramatically deepen our knowledge of the fundamental principles that govern the cosmos. Within popular culture, black holes have been represented in countless ways, often appearing in films and literature as terrifying gateways to other dimensions. It is vital, however, to differentiate this fiction from scientific fact, as most of these portrayals greatly magnify their actual properties and the dangers they pose. In the real universe, grasping how black holes truly function is essential to our overall comprehension of cosmology. Moreover, the very existence of black holes prompts profound philosophical inquiries. As a species, what does it signify that such bizarre and mighty objects are a part of our reality? Contemplating this question allows us to broaden our perspective on humanity's place in the cosmos. Ultimately, these are intricate and compelling phenomena that are frequently misrepresented, when in fact they are objects that defy our perceptions and inspire us to venture beyond the known. The next time you encounter the topic, I hope you'll remember that there is far more to them than meets the eye, and each new insight moves us closer to solving the great mystery of the universe. While the universe is filled with countless enigmas, one in particular is distinguished by its incredible power and its central role in shaping galaxies: the supermassive black hole. It's natural to ask how such colossal entities, capable of consuming everything in their path, including light itself, can even exist. This remains one of the most compelling questions I find myself pondering when we discuss these cosmic titans. To begin to grasp the nature of supermassive black holes, you must first know their whereabouts. These gargantuan objects are found at the core of nearly every galaxy, including our own Milky Way, and their mass can be billions of times greater than our sun's. Just try to conceive of a black hole containing the mass of 1,000,000 stars combined. This thought is not only captivating, but also points to their critical importance in the formation and evolution of galaxies. So, what function do these supermassive black holes serve in the cosmos? A leading theory proposes that they operate as gravitational anchors for the countless stars and vast clouds of gas that swirl around them. This suggests that in their absence, galaxies might simply fly apart into the void. In a way, you can think of supermassive black holes as the conductors of a grand cosmic orchestra, preserving balance and order across the universe. As galaxies take shape and evolve over eons, their central supermassive black holes appear to grow in tandem. This observation leads to a crucial question. Are these giants born this way, or do they grow by merging with smaller black holes over time? The answer remains elusive, with several theories suggesting they might begin as much smaller stellar black holes and gradually accumulate matter, eventually combining with others to become the behemoths that now anchor their galaxies. Regarding these mergers, it's fascinating to consider how such dynamics can shape a galaxy's entire evolutionary path. When two supermassive black holes collide, they generate powerful gravitational waves, which are essentially ripples in the structure of spacetime. These waves offer us invaluable clues about the universe's nature and the behavior of these cosmic giants. And learning to detect them has been a groundbreaking achievement in astrophysics that has redefined our understanding of the cosmos. It's also important to note that the activity of a supermassive black hole extends beyond merely swallowing matter. As material spirals inward, it can form a glowing accretion disk that heats up and radiates with incredible intensity. This emitted energy can be so powerful that it lights up the cosmos, making these disks some of the brightest objects in the universe. In fact, the most active of these are categorized as active galactic nuclei, or AGNs, which are essential for studying how galaxies interact and develop. The profound relationship between supermassive black holes and their host galaxies is an utterly captivating subject that beckons us to investigate the universe's greatest mysteries and our own position within it. There is substantial evidence indicating a correlation between the mass of a supermassive black hole and the total number of stars in its galaxy. This leads us to a fundamental question. Do the black holes orchestrate star formation, or do they themselves grow in response to the stars forming around them? Astrophysicists are actively researching the intricate equilibrium involving supermassive black holes. Investigating these cosmic phenomena not only gives you a glimpse into the universe's distant past, but also equips us to forecast its ultimate trajectory. As the cosmos continues its expansion, the interplay between galaxies and their central black holes could trigger further mergers and profound shifts in galactic architecture, much like a perpetual celestial ballet, where each step carries unforeseen implications. The study of supermassive black holes also introduces compelling philosophical inquiries. If these immense objects are capable of shaping the very evolution of galaxies, you have to wonder what this implies about our own significance in the universe. Their existence serves as a powerful reminder that we are inhabitants of a vast and perpetually transforming cosmos, governed by forces far beyond our comprehension. Moreover, gaining insight into supermassive black holes deepens our comprehension of physics itself. The extreme gravitational forces exerted by these entities defy our conventional models of space and time, forcing you to re-examine the most fundamental principles of physics. This leads to the captivating question that continues to puzzle scientists. Could gravity be the ultimate key to unlocking the universe's most profound secrets? As our technology progresses, astronomers are peeling back more layers of mystery surrounding the nature of supermassive black holes. Instruments like cutting-edge telescopes and sophisticated observational techniques allow you to scrutinize these giants in greater detail than ever before. Every new finding is akin to opening a portal to a deeper understanding of the cosmos, bringing to light secrets that have been concealed for billions of years. In essence, supermassive black holes represent much more than simple voids in the fabric of space. They are integral components of the cosmic web, influencing everything from the formation of galaxies to our core theories about gravity and time. These celestial titans persist in being a source of fascination and a profound challenge to human understanding. And as you continue to explore the universe, we are bound to uncover even more about their role in cosmic history, and perhaps our own destiny. So, what constitutes the life of a black hole? To explore this fascinating question, you must embark on a narrative that, while seemingly drawn from science fiction, is firmly grounded in the principles of physics and astrophysics. Let's begin by examining how a black hole's journey commences. It originates with a star of immense proportions, far exceeding the size of our own sun. As these giants exhaust their fuel and approach their demise, their cores give way to the overwhelming force of their own gravity, creating a remnant that can evolve into a black hole. But what follows this gravitational collapse? Picture a star as a balloon that, once pierced, rapidly deflates. For stars, however, this process is an incredibly violent and explosive event we call a supernova. This cataclysm not only signifies the star's end, but also disperses its material across space, seeding the surrounding cosmos with heavy elements. If the core left behind possesses sufficient mass, it becomes a black hole, a region in spacetime where gravity is so powerful that nothing, including light itself, can break free. Once formed, a black hole begins a new stage of its existence, feeding on any matter that drifts too close, like an insatiable cosmic predator. This accretion process allows black holes to devour stars and gas clouds, facilitating their growth and enabling them to become ever more massive over millions of years. However, nothing in the cosmos is truly eternal, and like stars, black holes possess their own life cycle, which can lead them to become the supermassive objects at the centers of galaxies. But you might wonder what happens when a black hole exhausts its supply of consumable matter. At this point, it transitions into a far more perplexing phase of decay. It may seem counterintuitive, but black holes are not immortal. According to the theory of Hawking radiation, first proposed by the renowned physicist Stephen Hawking, they can eventually evaporate, although this process is extraordinarily slow. It's as if the black hole is constantly perspiring energy in the form of particles. To understand this evaporation, you can imagine a black hole as a basin of hot water. Just as the water gradually turns to steam and disappears, a black hole slowly bleeds away its mass through Hawking radiation, a process that could ultimately result in its complete disappearance. This prospect naturally leads to a difficult question. What happens when a black hole has fully evaporated? The answer remains a subject of fierce debate among physicists. Over an immense span of time, a black hole might shrink until nothing is left. But can it truly vanish without a trace? Some scientists propose that it could leave behind a remnant of information, as the principles of quantum information theory suggest that information can never be destroyed. This creates a profound scientific and philosophical puzzle. If a black hole evaporates, where does all the information it once held actually go? It's a dilemma we are still striving to resolve. Furthermore, a black hole's life is rarely a solitary affair. Throughout its existence, it can become part of a binary system, where it orbits another black hole, sometimes leading to a spectacular merger. These cosmic collisions send out gravitational waves, ripples in the very fabric of spacetime, that your instruments here on Earth are now capable of detecting. The life of a black hole, therefore, has consequences that resonate not just in its immediate vicinity, but across the entire universe. Interestingly, despite their reputation for destruction, black holes also assume a vital creative function in the formation of galaxies. It is thought that their immense gravitational pull is instrumental in gathering the matter that fuels the birth of new stars and planetary systems. This makes you wonder if we should view black holes as creators, just as much as we see them as destroyers, a duality that lies at the very core of their nature. Ultimately, the existence of a black hole is an unending cycle of creation, growth, change, and possible annihilation, with each stage compelling you to question the universe and your own place within its grand design. The life story of a black hole is a profound allegory for the transient character of all existence, reminding us that even the most mysterious celestial objects follow a life cycle that may be deeply woven into the very fabric of the cosmos. As we contemplate the existence of these enigmatic phenomena, you realize that while they seem impossibly remote, black holes are a reflection of the universe's history and our own enduring quest to understand the unknown. The question of what the future holds for black holes is a captivating field of study, sparking curiosity in scientists and laypeople alike. To understand what destiny awaits these cosmic giants, it helps to view the life of a black hole as an epic saga. Each stage of its existence is marked by profound trials and transformations, beginning with its birth from the collapse of a massive star. But what follows this dramatic origin? Over immense spans of time, these black holes can expand by drawing in and consuming any matter in their vicinity. You can imagine a black hole as a perpetually hungry dragon, devouring everything that ventures too close and steadily accumulating more mass. Yet what happens when there is nothing left for it to consume? Does the dragon simply wait in hunger, or does it undergo a new transformation? One of the most compelling theories proposes that once a black hole depletes its supply of surrounding matter, it might actually start to evaporate. This process, known as Hawking radiation, introduces a mind-bending question. Can a black hole, one of the most dominant forces in the cosmos, actually fade away over time? Although this phenomenon is incredibly slow, potentially taking billions upon billions of years, it suggests that even black holes are not immortal. But what if a black hole were to find itself in an environment where the conditions changed radically? For example, if a nearby galaxy were to collide with our own, it could trigger an event that completely rewrites the black hole's life story. It raises the possibility of two black holes merging, creating an even larger entity. The concept of these cosmic titans engaging in a gravitational dance is truly mesmerizing and opens up a universe of new possibilities. Exploring the future of black holes more deeply brings up questions about their relationship with dark energy. This enigmatic force, which seems to be accelerating the expansion of the universe, might be fundamentally tied to the existence and fate of black holes. If dark energy continues to propel the cosmos toward an infinite expansion, will black holes eventually be scattered across the void, becoming isolated islands in an endless sea of nothingness? Among the most intriguing theories is the idea of the Big Rip, a scenario where the universe's expansion becomes so overpowering that it could ultimately tear apart even black holes. In this dramatic outcome, black holes, which have long reigned as titans of the cosmos, could be reduced to mere dust. This prospect forces us to ask, what really happens to black holes at the very end of time? The life cycle of a black hole also encourages us to think about its role in the greater evolution of the universe. If a black hole is capable of evaporating, what kind of legacy does it leave behind? Some scientists theorize that as they vanish, black holes could release some of the matter and energy they previously captured, thereby contributing to the formation of new stars and galaxies. This implies that the death of a black hole might, in fact, spark a new beginning for the cosmos. The future of black holes is not merely a subject of scientific inquiry. It also brings forth deep philosophical questions. If black holes can indeed disappear, what does this reveal about our understanding of time and matter? Are they truly indestructible, or are they just participants in a perpetual cycle of cosmic creation and destruction? The questions only multiply, and as we probe the universe, we come face to face with the reality that our answers may be as elusive as the black holes themselves. As science progresses, new technologies are enabling us to observe and analyze these phenomena in ways that were previously inconceivable. With every new finding, we uncover additional layers of complexity in the life of a black hole. This makes you wonder if we might one day discover that black holes have an even more fundamental role in the universe's structure than we currently imagine. Every new theory and discovery brings us a step closer to comprehending the ultimate fate of these cosmic behemoths. The reality, however, is that we still have so much more to learn. The story of a black hole, much like the story of any great hero, lacks a definitive conclusion. And that is precisely what makes it so captivating. Though the thought of a black hole vanishing might sound like a tragic end, it also serves as a poignant reminder of the universe's cyclical nature, where every conclusion is simply a new start. Therefore, the narrative of black holes continues, daring us to keep exploring and challenging everything we believe we know about reality. The next time you look up at the star-filled sky, remember that black holes are not just devourers of matter, but are essential players in the cosmic story of the universe. Investigating their future is not only a journey of scientific discovery, but also a chance to reflect on our own place within this vast and mysterious cosmos. As their story continues to unfold, full of wonders that invite us to keep dreaming and searching for answers. Now, what if I told you that black holes and dark energy are like two lead actors on the cosmic stage, and that their interactions could fundamentally reshape our entire understanding of the universe? While they may seem like entirely separate concepts at first, they are interconnected in surprising ways across the immense expanse of the cosmos. To start, it's crucial to understand what dark energy actually is. Imagine you are standing in a pitch-black room. Although you can't see a thing, you can feel an invisible pressure pushing the walls outward. This mysterious force, which appears to be stretching space itself, is what we refer to as dark energy. It is believed to constitute about 73% of the entire universe. But you may be asking, why is this significant to our conversation about black holes? After all, black holes are defined as regions of space where gravity is so powerful that nothing, not even light, can break free. Given this, how could these two seemingly opposite concepts possibly be connected? Fundamentally, black holes and dark energy are two pieces of the same cosmic puzzle. Where black holes serve to attract and accumulate matter, dark energy seems to do the opposite, propelling galaxies outward and fueling the universe's accelerated expansion. This dynamic establishes a cosmic interplay between the forces of attraction and repulsion. This raises a compelling question. Is it possible for black holes to influence dark energy? Certain theories propose that the incredible concentration of mass and energy within a black hole could alter dark energy in its immediate vicinity. You can think of a black hole as a powerful magnet placed within a field of invisible forces. While it pulls everything toward itself, it might also affect how dark energy operates around it. Another fascinating question comes up as black holes continue to expand by consuming the matter and energy that surrounds them. What becomes of dark energy in this process? Some scientists speculate that when a black hole devours matter, that material could be converted into dark energy, thus fueling its own expansive force. It's a concept where dark energy seems to thrive on the very chaos that black holes generate. One of the most captivating theories suggests that the interaction between these two cosmic giants could be the very key to deciphering the accelerating expansion of the universe. Can we witness a direct conflict between the gravitational influence of black holes and the repulsive nature of dark energy? Imagine a celestial struggle where each force attempts to assert its dominance over the cosmos, with gravity trying to consolidate matter and dark energy working to push it apart. This cosmic tension may also have profound effects on how we understand the universe's structure. Black holes might operate as catalysts that shape the distribution of dark energy throughout the cosmos. By gathering matter and energy around them, they could generate vast regions of lower density, where dark energy's repulsive effect becomes supreme, driving galaxies even farther from one another. However, this relationship isn't purely about chaos and conflict. A number of researchers are convinced that the link between black holes and dark energy could usher in new eras in our comprehension of physics. This leads to foundational questions for future study, such as whether black holes hold clues to dark energy's true nature, or if there is a delicate equilibrium between these two forces that we simply don't yet perceive. At its heart, this exploration is just beginning, and we are only starting to unravel these profound mysteries. As our technology improves and we gather more data from space, we may discover new and even more astounding connections between black holes and dark energy. Each new finding is like turning another page in a great cosmic book that is still being written. So, what is the precise role that black holes play in the expansion of our universe? Although we are far from having complete answers, Every piece of evidence suggests they are intricately woven into the fabric of cosmic history. It's possible that in the future, we will discover how these opposing forces cooperate in a subtle balance that truly defines the nature of existence. As our exploration continues, it's vital that you and I keep an open mind to all possibilities. The connection between black holes and dark energy could do more than just change our view of the universe. It might also revolutionize our understanding of the physical laws that govern it. This is a powerful reminder that in the search for answers, we often find even more questions that propel us toward new adventures in the incredible field of astrophysics. With every breakthrough, we move one step closer to grasping the grand design of reality. The relationship between black holes and dark energy reveals that the universe is a place brimming with surprises, where each piece of the puzzle is essential to seeing the complete picture. The next time you gaze up at the night sky, remember that far beyond those points of light, there is a universe more complex than we can possibly imagine. The existence of black holes doesn't just raise scientific questions about the physics of the cosmos. It also opens up a vast field for philosophical and ethical contemplation. What does it mean for us as human beings that such enigmatic and powerful entities are real? The very nature of black holes forces us to confront the fragility of our own knowledge and our grasp of the universe. You should consider for a moment that everything you know and experience could be just an infinitesimal fraction of all reality. With their capacity to trap all light and matter that comes near, black holes embody a mystery that challenges our concepts of existence itself and impacts how we see our own place in the cosmos. If there truly are regions in space where the laws of physics as we know them completely break down, what does that reveal about our own comprehension of reality? Philosophy has always been a quest to understand the purpose and meaning of our lives, and in this light, black holes compel us to question the very fabric of existence. Are they simply astronomical objects, or do they signify something far deeper? Perhaps they are a reminder that, despite all our scientific progress, a vast unknown still beckons to be explored, a thought that can be both intimidating and deeply inspiring. The idea that so much remains to be discovered can motivate us to continue pushing the boundaries of our knowledge. This thought can inspire you to keep exploring and broadening your own horizons. Moreover, the reality of black holes brings up questions about the nature of time and destiny. If time itself behaves differently in the vicinity of a black hole, how does that transform our perspective on life and death? The possibility that time comes to a halt at the singularity makes our own lives seem incredibly fleeting by comparison, which should prompt you to reflect on how you value your time and the choices you make in life. The grandeur of the universe poses questions that often seem plucked from a science fiction novel. What are black holes, really? Are they portals to other worlds, or simply cosmic monsters devouring everything in their path? Throughout this discussion, we have explored the fascinating nature of these spatial enigmas, and now it is time to reflect on their significance and what they can tell us about our place in the cosmos. Black holes offer you a window into the unknown, inviting you to question what you consider to be knowledge. Imagine that each one is a mirror, reflecting not only the vastness of the universe, but also the fragility of our own understanding. When faced with the immense and mysterious cosmos, who are we? The existence of these phenomena reminds you of how small we are, and yet how intensely curious we can be. The importance of exploring black holes extends beyond mere scientific curiosity. Each discovery we make brings us one step closer to understanding the fundamental laws that govern the universe. What secrets do they hold within them? What will they reveal about the creation of the cosmos or the ultimate fate of everything you know? Reflecting on these questions, you confront the very essence of existence. Often, black holes are perceived as merely terrifying objects to be avoided. In reality, however, they are foundational to the formation of galaxies. Isn't it astonishing to think that without them, the universe as you know it might be entirely different? The gravity of a black hole acts as a kind of cosmic anchor, pulling matter together and shaping celestial structures over billions of years. Who would have thought that a monster could also be an architect of the universe? As we deepen our understanding of these cosmic giants, philosophical dilemmas also arise. What does the existence of black holes mean for your perception of time and space? Relativity teaches us that time can behave strangely near a black hole, which in turn invites you to ask, what is time really? Delving into these mysteries, you find yourself at the intersection where science and philosophy meet. Reflecting on this, you might ask, are we part of an eternal cycle of creation and destruction, or are we doomed to vanish into an abyss of darkness? These questions encourage you to consider your own existence within the context of cosmic time. The idea that black holes might evaporate over time, according to Hawking radiation, prompts you to reflect on the concept of finitude in an otherwise infinite universe. Contemplating our own mortality in light of these phenomena can be both sobering and liberating. When it comes to black holes, it is also important to consider their impact on culture and society. The portrayal of these phenomena in films, books, and other media often blurs the line between science and fiction, which can lead to misunderstandings about what we truly know. Reflecting on this can help you distinguish between science and speculation, and can foster critical thinking throughout society. Furthermore, black holes confront us with the ethics of cosmic exploration. As humanity advances in its quest to understand the universe, questions arise about our responsibility toward the cosmos. If we develop the technologies needed to travel to regions near these cosmic mysteries, should we do so? What consequences might this have for our species and for any ecosystems we might encounter? These are questions you cannot ignore. The search for answers about black holes urges you to consider the role we play in the universe. Are we merely observers, or are we also active participants in their narrative? Science invites you to become part of this grand cosmic story, where each discovery can change your perception of life and the universe, leading to deep introspection about what we value and where we are heading as a civilization. Finally, reflecting on black holes, it is important to remember that, despite their overwhelming nature, they offer you a unique opportunity to bridge science with philosophy. They challenge you to think beyond the known and explore the possibilities of the unknown. In a world where we often feel lost, these cosmic entities remind us that mystery is a fundamental part of existence. As you continue to explore these mysteries, it is vital to maintain a spirit of curiosity, because the universe still has much to teach us. It is essential, however, that you also recognize the myths that have developed around these phenomena. You will find that popular culture frequently paints a distorted picture, making it our duty to find the truth behind the fiction. Think about how often you allow stories to shape your perception of reality. Science, by its very nature, encourages you to be inquisitive and to challenge the information you are presented with. Every black hole possesses its own unique story, a complete arc from its creation to its eventual dissipation. Within this cosmic life cycle, you can find profound lessons about the transient nature of all existence. When you contemplate what their existence can teach us about our own lives and the universe's journey, you are inevitably faced with the truth that everything, from the most minuscule to the most magnificent, is interconnected. Black holes also push you to confront the ethical dimensions of our relentless search for knowledge. You have to ask yourself if we are truly prepared for the discoveries that may be waiting for us. While science possesses the power to revolutionize our comprehension of the world, it is accompanied by a significant weight of responsibility. In our pursuit of what is real, you must stay conscious of how that truth could affect our lives and our entire society. Looking ahead, the continued study of black holes promises to unlock entirely new ways of understanding the universe. Where might this journey of discovery take us? Human curiosity is fundamentally limitless, and as you will see, every single answer we uncover only leads to a new set of questions. Your exploration of the cosmos is a perpetual journey that calls on you to keep advancing, to never cease questioning, and to always continue learning. In the end, black holes represent much more than just objects in space. They have become powerful symbols of our quest for knowledge and our struggle to understand the universe. They inspire you to look up at the heavens with both awe and humility, serving as a reminder that while you may be a small part of a vast cosmos, your curiosity can lead to the discovery of unimaginable wonders. As I conclude, I want you to remember that every question that surfaces is another opportunity to continue exploring, learning, and marveling at the universe's great mysteries.